You are watching yourself pour milk into coffee. The white spiral blooms outward, threads dissolving into brown. You have seen this 1,000 times, but here is what you have never considered. Nothing in the fundamental laws of physics says this must happen in this direction. Run the film backwards. Watch the brown liquid spontaneously separate, white streams gathering themselves from the chaos, retreating into the jug. The mathematics works perfectly. Every equation is satisfied. The physics of your morning coffee permits something you have never witnessed and never will. You have never seen milk unmix. You have never watched a broken egg reassemble itself, shell fragments leaping from the floor to seal seamlessly around reconstituted yolk. These reversals are not forbidden by physics. They are merely so astronomically improbable that the universe would grow old and cold before you witnessed one. This is the arrow of time, and it points, always and everywhere, in one direction only. But why? The question sounds almost childish. Time moves forward because it does. But this is no answer at all. It is like asking why apples fall, and replying that falling is what apples do. As we shall see, the arrow of time is not written into the laws of nature. It emerges from something far stranger, something that traces back 14 billion years to the very beginning of everything. And understanding it will transform how you perceive every moment of your existence. You are watching yourself pour milk into coffee. The white spiral blooms outward, threads dissolving into brown, cream dispersing through dark liquid in patterns you have seen 1,000 times. It is the most ordinary thing in the world. You have never given it a moment's thought. But here is what you have never considered. Nothing in the fundamental laws of physics says this must happen in this direction. Run the film backwards. Watch the brown liquid spontaneously separate, white streams gathering themselves from the chaos, retreating upward into the jug as though remembering where they came from. The mathematics that governs every atom in that cup, every collision, every molecular interaction works equally well in reverse. The equations of physics are time symmetric. They do not care which way the clock runs. And yet, you have never seen milk unmix. Not once. Not ever. You have never watched a broken egg reassemble itself, shell fragments leaping from the floor to seal seamlessly around reconstituted yolk. You have never observed a corpse grow younger, wrinkles smoothing, hair darkening, muscles strengthening, until a baby crawls backwards into the womb. These reversals are not forbidden by the laws of nature. They are merely so astronomically improbable that the universe would grow old and cold, every star burning out, every galaxy dissolving, before you witnessed a single one. This is the arrow of time. It points, always and everywhere, in one direction only. We ride this arrow from birth to death, from memory to anticipation, from the Big Bang to the slow dimming of the final stars. We are so immersed in it that we cannot imagine existence without it. Cause precedes effect. Yesterday is fixed, while tomorrow remains open. The past is gone, and the future is coming. But why? The question sounds almost childish. Time moves forward because it does. Because that is what time means. But this is no answer at all. It is like asking why apples fall, and replying that falling is what apples do. We have described our experience without explaining it. We have mistaken a label for an answer. Consider what physics actually tells us. Film 2 billiard balls colliding on a table, the click of contact, the transfer of momentum, the balls rolling away at new angles. Now run the film backwards. 2 balls roll toward each other, click and separate. Both versions obey Newton's laws perfectly. Both are physically valid. There is nothing in the equations that prefers one direction over the other. The same holds for every fundamental theory we have discovered. Maxwell's electromagnetism works forwards and backwards. Schrödinger's quantum mechanics does not distinguish past from future. Einstein's relativity treats time as a dimension through which one might, in principle, move either way. At the deepest level we have probed, nature appears profoundly indifferent to whether time runs forward or backward. Yet our experience screams otherwise. Every morning you wake older than you were. Your coffee cools, never spontaneously heats. Memories accumulate of yesterday, but not tomorrow. The newspaper reports what happened, not what will happen. The entire structure of your existence, anticipation, regret, hope, nostalgia, depends on a distinction between past and future that physics cannot find. This is remarkable. This demands explanation. Imagine filming your entire day, waking, eating, working, speaking, sleeping, then playing the whole thing in reverse. Physically, mathematically, every frame of that backwards film would be valid. Digested food could reassemble on plates. Spoken words could re-enter mouths. Sound waves converging from walls to compress air in throats. Exhaled carbon dioxide could gather from the atmosphere and return to lungs. The physics permits it all. Yet you know, with absolute certainty, that this backwards film depicts something impossible. Not merely unlikely. Impossible. But if the laws of physics allow it, what forbids it? This is the puzzle we shall investigate. The arrow of time is not written into the fundamental equations of the universe. It emerges from something else entirely, something stranger and more profound than we might have guessed. As we shall see, the direction of time is not a law. It is a consequence, and understanding where it comes from will transform how you perceive every moment of your existence. The puzzle deepens when we look more closely at what we mean by time's direction. We actually observe not one arrow, but three, and they all point the same way. This alignment is not obvious. It is not inevitable. It is a clue. The first arrow is thermodynamic. Entropy, the measure of disorder, always increases. Milk mixes into coffee, but never unmixes. Ice melts, but water does not spontaneously freeze in a warm room. Buildings crumble. Rubble does not spontaneously assemble into buildings. This is the second law of thermodynamics, perhaps the most universal pattern we have ever discovered. Disorder grows. Systems run down. The universe, it seems, prefers chaos to order. The second arrow is psychological. We remember the past and anticipate the future, never the reverse. You can recall what you ate for breakfast, but not what you will eat for dinner. Your memories point backwards, your plans point forwards. This asymmetry is so fundamental to consciousness that we cannot truly imagine what it would mean to experience time differently. The psychological arrow defines what past and future mean to us. The third arrow is cosmological. The universe expands. 14 billion years ago, everything was compressed into an unimaginably hot, dense state. Ever since, space itself has been stretching, galaxies receding from one another, the cosmos growing larger and colder. This expansion has a direction, from dense past to sparse future. The universe, like us, appears to be going somewhere. Now here is the question that should keep you awake. Why do all three arrows point the same way? Think of it like this. Imagine 3 compass needles in separate rooms, each responding to different forces, magnetism in one, gravity in another, wind in the third. You check each room and find all 3 needles pointing north. Coincidence? Perhaps. But you would want to investigate. You would suspect a hidden connection. The three arrows of time are like those needles. Thermodynamics, psychology, and cosmology appear to be independent domains, one governed by statistical mechanics, one by neuroscience, one by general relativity. Yet all three point the same direction. All three agree that past and future are profoundly different, and they agree on which is which. This cannot be accident. Something coordinates them. We might try to explain them separately. Entropy increases because, well, that is the second law. Memory points pastward because that is what memory means. The universe expands because that is what observations show. But these are not explanations. They are restatements. We have described the arrows without explaining why they exist or why they align. Let us push harder on one of them. Consider the thermodynamic arrow, since it seems the most fundamental. Why does entropy increase? The conventional answer invokes probability. There are vastly more ways for a system to be disordered than ordered. If a system explores its possible states randomly, it will almost certainly end up disordered. Not because anything pushes it there, but because disorder is where almost all the possibilities live. High entropy wins by sheer numerical dominance. This sounds satisfying, but here is the problem. This probabilistic reasoning works equally well in both directions of time. If we find a system in a high entropy state now and reason statistically, we should expect entropy to have been even higher in the past. Random fluctuations toward order should be equally rare whether we look forward or backward. The statistical argument, by itself, predicts that the past was disordered too, but this contradicts everything we know. The past was more ordered than the present. Yesterday's egg was intact. Today's is scrambled. The statistical explanation tells us something important about how entropy increases, but it cannot tell us why it was ever low to begin with. We have confused description with explanation once again. The three arrows align. They must have a common origin. Something breaks the symmetry between past and future, something that statistics alone cannot provide. To find it, we must look not at the laws of physics, which are time-symmetric, but at something else entirely. We must look at how the universe began. Before we can understand why entropy was low in the past, we must understand what entropy actually measures. The word is often associated with disorder, but this is vague. What does disorder mean, precisely? And why should the universe care about it? The answer lies in counting. Consider a deck of cards. There are approximately 10 to the 68th power possible arrangements, more arrangements than there are atoms in the observable universe. Among all these possibilities, how many are ordered in some meaningful sense? Precious few. One arrangement has all cards sorted by suit and rank. A handful more might spell out messages or form patterns. The overwhelming majority look random. Now imagine shuffling a sorted deck. After one shuffle, it is probably still somewhat organized. After 100 shuffles, it is almost certainly disordered. This happens not because shuffling prefers chaos. The shuffle is random, treating all arrangements equally. It happens because ordered arrangements are vanishingly rare. If you explore configurations at random, you will almost certainly end up somewhere disordered. This is entropy in a nutshell. Entropy measures not disorder in some vague aesthetic sense, but the number of microscopic arrangements compatible with what we observe macroscopically. A tidy room has low entropy because there are relatively few ways to arrange objects tidily. A messy room has high entropy because there are vastly more ways to scatter things randomly. The same applies to your coffee. When milk and coffee are separated, the molecules can only be arranged in certain ways. When they are mixed, The molecules can be arranged in enormously more ways. The milk molecules dispersed throughout, each in any of millions of possible positions. Mixed states vastly outnumber separated states. The milk mixes because mixing is where almost all the possibilities are. This is the second law of thermodynamics, and it is not really a law at all, not in the sense that conservation of energy is a law. It is a statistical truth. Systems evolve toward high entropy because high entropy is overwhelmingly probable. Nothing pushes them there. They simply find themselves in the region where almost all states live. In principle, milk could spontaneously unmix. Every molecule might, by chance, happen to move in just the right direction to gather back together. The probability is not zero, but it is so small that waiting for it would require patience exceeding the age of the universe by factors that make the national debt look modest. For all practical purposes, it will never happen. But here is where the reasoning breaks down. Statistics treats past and future symmetrically. If we observe a mixed cup of coffee and reason probabilistically, we should conclude that it was probably mixed 5 minutes ago too, and 5 minutes before that. Random fluctuations toward order are rare in both temporal directions. The statistical argument predicts maximum disorder in the past as well as the future. Yet we know this is false. 5 minutes ago, the milk was in the jug and the coffee was black. 10 minutes ago, the coffee was hot and the beans were whole. An hour ago, the beans were on a plant in Colombia. The past was more ordered than the present, not less. The statistical argument gets the past completely wrong. This is not a minor problem. This is the central puzzle. Probability explains how entropy increases given that it starts low, but probability alone cannot explain why it ever started low. If we reason purely from statistics, we should expect to find ourselves in a universe that has always been disordered, fluctuating randomly around maximum entropy. Instead, we find ourselves in a universe with a highly ordered past, entropy steadily increasing, from then toward now and beyond. Something breaks the symmetry, something makes the past special, and that something is not contained in the laws of physics, which are time-symmetric, nor in statistical reasoning, which treats directions equally. The missing ingredient is an initial condition. The universe did not merely happen to have low entropy in the past. It began that way. And that beginning, as we shall discover, explains everything. 14 billion years ago, the universe existed in a state of extraordinary order. This may seem counterintuitive. We picture the Big Bang as an explosion, chaotic, violent, random. But chaos is not the same as disorder in the thermodynamic sense. The early universe was unimaginably hot and dense, yes, but it was also astonishingly smooth. Matter and energy were distributed with near-perfect uniformity, varying by only 1 part in 100,000. This smoothness represents a state of extremely low entropy. We have direct evidence of this. The cosmic microwave background radiation, the afterglow of the Big Bang, released when the universe was about 380,000 years old, is uniform to extraordinary precision. This baby picture of the cosmos shows us what the early universe looked like, and what it looked like was tidy, smooth, ordered. This changes everything. The arrow of time emerges not from the laws of physics, which are time-symmetric, but from the boundary conditions, the way the universe happened to start. Given that the cosmos began in a low-entropy state, statistical reasoning correctly predicts that entropy will increase toward the future. The direction of time is not a law. It is a consequence of initial conditions. Think of it this way. Imagine a box containing gas molecules, all clustered in one corner. Release them. They spread throughout the container, not because anything pushes them, but because there are vastly more spread out configurations than clustered ones. An arrow of time appears. The box evolves from ordered, clustered, to disordered, spread out. But notice, the arrow emerged because we started with molecules in the corner. If we had started with molecules already spread evenly throughout, nothing interesting would happen. The gas would remain spread out, fluctuating randomly with no discernible direction. No arrow. The initial condition creates the arrow. Now expand this reasoning to the entire cosmos. The Big Bang was the universe's gas in the corner moment. Everything began compressed, smooth, special. Ever since, entropy has been increasing, matter clumping into galaxies, stars igniting and burning out, planets forming and cooling, complexity emerging and eventually dissipating. The arrow of time exists because we started wound tight. This is what physicists call the past hypothesis, the assumption that the universe began in a low entropy state. It is not derived from the laws of physics. It is added to them, an initial condition that when combined with time-symmetric laws and statistical reasoning produces the arrow we observe. Every irreversible process you have ever witnessed, every cooling cup of coffee, every aging body, every fading memory is drawing down the thermodynamic capital invested at the Big Bang. We are not creating disorder. We are spending an inheritance. The second law of thermodynamics is not truly a law in the sense of F = ma or E = mc2. It is a consequence of probability plus boundary conditions. Given how the universe began, entropy increase is overwhelmingly likely. But the beginning itself is not explained by statistics. The beginning is the unexplained foundation on which everything else rests. Here is something remarkable to consider. For gravity, entropy works differently than for ordinary matter. When gas spreads out, entropy increases. But when matter under gravity clumps together, entropy also increases. The smooth early universe was gravitationally low entropy. Stars and galaxies represent entropy increasing as matter clumps under gravitational attraction. This explains the cosmological arrow. The universe expands because it began smooth, and gravitational clumping represents entropy increase. The thermodynamic and cosmological arrows align because they trace back to the same source, the extraordinary smoothness of the early universe. The wound clock is running down. Galaxies form, stars burn, planets cool, life emerges and eventually dies, and entropy rises inexorably toward eventual equilibrium. We live in the long exhale following the Big Bang's initial inhalation. Every moment you experience is part of this cosmic unfolding. The arrow that carries you from birth to death, from memory to anticipation, from cause to effect, was aimed at the dawn of creation. You are riding a wave that began 14 billion years ago, when the universe was young and tidy and full of potential. The question now becomes, why was the Big Bang so special? We have traced the arrow of time to its source. The T, direction of past and future, emerges from the universe's initial conditions, the extraordinary smoothness and low entropy of the Big Bang. Given that beginning, everything else follows. Entropy increases, memory points pastward, the cosmos expands. But this creates a new question, perhaps the deepest we can ask. Why did the universe begin so ordered? The second law tells us that low entropy states are improbable. By definition, they are rare among all possible configurations. The smooth, uniform Big Bang was an extraordinarily special state, as improbable as finding a shuffled deck perfectly sorted, multiplied by itself many times over. Such states do not happen by chance. Yet, it happened. The universe began that way. Why? The honest answer is, we do not know. This may be unsatisfying, but it is important. Science proceeds by acknowledging what remains unexplained. The arrow of time rests on a foundation we do not yet understand. This is not failure. This is the frontier. Some physicists invoke cosmic inflation, a period of exponential expansion in the universe's earliest moments that would smooth out any initial irregularities. Inflation might explain why the cosmos became so uniform, but inflation itself requires specific initial conditions. We may have moved the mystery rather than solved it. Others appeal to quantum cosmology, attempts to derive the universe's initial state from quantum principles. Perhaps the wave function of the universe has a natural boundary condition that makes low-entropy beginnings more probable or inevitable. These approaches are speculative, mathematically sophisticated, and far from settled. Still others suggest that the initial conditions may simply be brute facts, boundary conditions that cannot be further explained, like the fundamental constants of nature. We do not know why the electron has the mass it does. Perhaps we cannot know why the universe began as it did. This is intellectually uncomfortable, but may be correct. There is also the possibility of selection effects. If there are many universes with different initial conditions, perhaps observers like us can only exist in those with low entropy beginnings. We would inevitably find ourselves in an ordered universe because disordered universes cannot produce observers to notice them. This anthropic reasoning is controversial. It explains why we observe what we observe without explaining why it exists in the first place. The mystery demands humility. What we know is this: the arrow of time is not a fundamental feature of reality. It emerges from initial conditions. Time-symmetric laws, combined with statistical reasoning, produce an arrow only when given a special starting point. The Big Bang provided that starting point. Without it, there would be no direction to time, no distinction between past and future, no foundation for memory or causation or change. We are patterns that exist because the universe began wound tight. The arrow is our inheritance, and the source of that inheritance remains unexplained. This should not diminish our wonder, it should deepen it. That we can trace the arrow back to cosmic origins, that we can understand the mechanism even while the ultimate cause eludes us, that evolved primates on a minor planet can ask such questions at all. This is extraordinary. The universe is under no obligation to make sense to us. Yet it does, at least in part. We have learned where the arrow comes from. Now we must understand how it manifests, how a cosmic initial condition translates into your experience of remembering the past, into your sense that causes precede effects, into the expansion of space itself. The three arrows we identified at the start, thermodynamic, psychological, cosmological, all trace back to the Big Bang. But how exactly do they connect? How does entropy in the early universe become memory in your brain? The unity of the arrows awaits. You remember what you ate for breakfast. You do not remember what you will eat for dinner. This seems obvious, so obvious that it barely warrants mention. Of course we remember the past. That is what memory means. But consider for a moment how strange this is. Why should memory point in one direction rather than the other? What makes the past accessible to recollection while the future remains opaque? The answer lies in thermodynamics. Memory is not separate from physics. It emerges from it. A memory is a physical thing. It is a correlation between your current brain state and events that occurred at another time. When you remember your 10th birthday party, certain neural patterns are active, patterns that were created by light entering your eyes, sound waves vibrating your eardrums, experiences being encoded in synaptic connections. The memory exists because a physical process created it, and here is the crucial point. Creating a memory increases entropy. Think of a camera recording a scene. The camera captures order, light patterns from the environment and stores them on film or sensor. But recording is not free. The camera generates heat, the battery drains, entropy increases somewhere in the system. The photograph exists because disorder increased to create it. Your brain works the same way. When you form a memory, photons strike your retinas, triggering cascades of neural activity, strengthening some synaptic connections while weakening others. Each step involves energy transformations. Each step generates heat. Each step increases entropy. Recording information is thermodynamically irreversible. This is not a minor technical detail. This is why the psychological arrow aligns with the thermodynamic arrow. We remember the direction in which entropy increases because remembering is itself an entropy increasing process. Our memories point toward lower entropy, toward the past, because that is the direction from which information can flow into physical recording systems. The past leaves traces precisely because trace leaving increases entropy. Could we, in principle, remember the future? Not through physics. A brain that remembered tomorrow would require information to flow from high entropy to low, would require local decreases in entropy without corresponding increases elsewhere. This would violate the boundary conditions set at the Big Bang. Such a brain could not exist in our universe. Imagine a being whose memory pointed futureward, who recalled tomorrow and anticipated yesterday. From its perspective, what we call the future would be its past. It would experience time as flowing in the opposite direction. But could such a being exist? No. Memory formation requires entropy increase. If entropy increases toward what we call the future, then memories must form toward what we call the past. The future-ward remembering being is not merely unlikely. It is physically impossible given our universe's boundary conditions. This is profound. Your most intimate experience of time, the vivid difference between remembering and anticipating, between nostalgia and hope, between regrets and planning, emerges from cosmic physics. The psychological arrow is not separate from the thermodynamic arrow. It is entailed by it. When you recall a vivid memory, your first kiss, the smell of your grandmother's kitchen, the sound of a song that meant something, you are experiencing the arrow of time from the inside. That memory exists because photons entered your eyes, because neurons fired, because synapses changed, because entropy increased. The memory is a physical trace, a fossil of experience, created by irreversible processes that trace back, ultimately, to the Big Bang's special conditions. You cannot remember tomorrow's sunset. This is not a limitation of human cognition. It is a constraint imposed by the structure of time itself. The psychological arrow points the same direction as the thermodynamic arrow, because they are the same arrow, experienced from different vantage points. One describes the physics, the other describes what the physics feels like from the inside. We remember the past because the past is where entropy was lower, and memory creation requires entropy increase. Your sense of time passing, your conviction that yesterday is gone and tomorrow is coming, your entire experience of temporal flow This is thermodynamics in action, operating in the neurons of an evolved primate, making the abstract arrow of time into something lived and felt. The cosmos set the conditions. Your brain enacts the consequences, and you experience the result as the most fundamental feature of conscious existence. The difference between what was and what will be. A glass falls from a table. It shatters on the floor. We say the fall caused the shattering, but physics is time-symmetric. The equations permit shards assembling themselves into a glass that leaps to the table. Why does cause precede effect? Why not the reverse? The answer, once again, is entropy. Causes are low-entropy states. Effects are high-entropy states. The intact glass, sitting on the table, is ordered, its molecules arranged in a specific crystalline structure, its position stable and defined. The shattered glass, scattered across the floor, is disordered, fragments in random positions, molecular bonds broken, structure dissolved. The evolution from intact to shattered is entropy increasing. The reverse evolution would be entropy decreasing. We never see shards spontaneously assemble because that would require an astronomically improbable decrease in entropy. Causation has a direction because entropy has a direction, and entropy has a direction because of the Big Bang. This resolves an ancient puzzle. Philosophers have long debated what causation really means, why it flows one way, whether it is a fundamental feature of reality or merely a pattern we impose. The answer is thermodynamic. Causation is the entropic arrow experienced through the lens of individual events. Causes precede effects because low entropy precedes high entropy in our universe. The same reasoning explains why evidence points to the past rather than the future. Fossils exist because fossilization increased entropy. Light from distant stars reaches our telescopes because stellar processes increased entropy. Photographs preserve moments because photography increased entropy. Every record of the past exists because creating it was thermodynamically irreversible. We can study history, but not futurography. We can examine fossils of dinosaurs, but not fossils of creatures yet to evolve. This is not because the future is somehow less real than the past. It is because records can only point toward lower entropy, and lower entropy lies in the past. The entire edifice of historical knowledge, of science itself, depends on this asymmetry. We can only know about times when entropy was lower than it is now. The future is unknowable, not merely because it has not happened yet, but because no evidence of it can exist. Evidence creation is irreversible. Evidence therefore points pastward only. Now consider the cosmological arrow, the expansion of the universe. Galaxies recede from one another. Space itself stretches. The cosmos grows larger and colder over time. This expansion has a direction, from the dense hot past toward the sparse cold future. How does this connect to entropy? For gravity, entropy works differently than for ordinary matter. When gas in a box spreads out, entropy increases. But when matter under gravitational attraction clumps together, entropy also increases. The smooth early universe was gravitationally low entropy. The clumpy universe of today, with galaxies, stars and black holes, represents entropy increasing as gravity does its work. The cosmological arrow reflects gravitational entropy. The universe expands because it began smooth, and gravitational evolution toward clumpiness is entropy increasing. Cosmic expansion is not a separate phenomenon from thermodynamic irreversibility. It is the same phenomenon writ large across the cosmos. All three arrows now converge. The thermodynamic arrow, entropy, increases from the low-entropy Big Bang toward high-entropy equilibrium. The psychological arrow. Memory forms in the direction of entropy increase, pointing toward lower entropy in the past. The cosmological arrow. The universe expands as gravitational entropy rises from the smooth initial state. 3 manifestations. 1 source. The arrows align because they must, because they all emerge from the same boundary conditions, the same special beginning, the same wound clock running down. What seemed like separate mysteries resolve into unity, causation, memory, cosmic expansion, all faces of a single underlying reality. The universe is more coherent than we might have guessed. Time's direction, in all its manifestations, traces to one source, the extraordinarily special conditions of the Big Bang. We set out to understand why time moves forward. We have found that the question itself needed refinement. Time does not move. There is no cosmic clock ticking. What we call time's direction is the relationship between entropy and the universe's boundary conditions. The arrow emerges from how the universe began. The 3 compass needles in their separate rooms all pointed north because a single magnetic field affected all of them. The 3 arrows of time all point the same direction because a single cosmic fact, the low-entropy Big Bang, underlies them all. The unity is complete. Now we must understand what it means. We have traced the arrow of time from coffee cups to cosmic origins and back again. We understand the mechanism, low-entropy initial conditions, statistical evolution toward higher entropy, the alignment of thermodynamic, psychological, and cosmological arrows. But understanding the mechanism is not the same as grasping the significance. What does the arrow of time mean for existence itself? Consider a river flowing downhill. Water moves from gravitational potential toward equilibrium, from high ground to low. Along the way, the flow can power mills, carve canyons, nourish ecosystems. Structure emerges because there is gradient to exploit. Without the downhill slope, water would pool and stagnate. No flow, no mills, no canyons, no life. The universe is like that river. Entropy flows from the Big Bang's low state toward eventual equilibrium, from order to disorder, from special to generic. Along the way, the flow permits everything we see and are. Galaxies form, stars ignite, planets coalesce, life emerges. We are eddies in the entropic current, temporary patterns sustained by the gradient, structures that exist because entropy increases. This is not metaphor. It is physics. Every living organism is an entropy machine. You eat food, complex molecules assembled by plants and animals, ordered structures full of chemical energy. You digest it, breaking down the order, extracting energy to maintain your own structure. You excrete waste, simpler molecules, higher entropy. You radiate heat into your surroundings. The net result? You maintain your exquisite internal order by exporting disorder to the environment. You locally decrease entropy by globally increasing it. You are a pattern that persists by accelerating the universe's march toward equilibrium. This applies to everything organized: ecosystems, civilizations, computers, books. All are local decreases in entropy paid for by larger increases elsewhere. Structure requires gradient. Gradient requires special initial conditions. The arrow of time is not merely something we experience. It is the condition for our existence. Without time's direction, there will be no evolution, no selection pressure driving increasing complexity. Without time's direction, there would be no chemistry, no irreversible reactions building molecules of life. Without time's direction, There would be no minds, no memory formation, no learning, no thought. We are patterns that exist because the arrow exists. Consider your own morning. You wake, neural patterns maintained by metabolism, body temperature held steady by chemical reactions that export heat. You eat, importing order, exporting entropy. You think, information processing that generates waste heat. Neural computation that increases entropy in your brain and environment. Every action you take participates in the universe's evolution from its ordered beginning. You are not separate from cosmic physics. You are cosmic physics, the universe organized temporarily into a pattern that can contemplate itself. This is perhaps the deepest insight the arrow of time offers. We are the universe understanding itself. Matter, arranged by 14 billion years of entropy, increase has become complex enough to ask why entropy increases. Atoms have organized into structures that wonder about atoms. This could not happen without the arrow. In a universe at equilibrium, maximum entropy, no gradients, no structure, nothing would ever happen. No stars would form, no planets would coalesce, no life would emerge. Such a universe would be static, featureless, dead. Not dramatically dead, with explosions and catastrophe. Just eternally, boringly same. Nothing changing because nothing could change. The arrow makes possible everything that is not sameness. Change requires gradient. Life requires change. Mind requires life. Wonder requires mind. We exist in the long, interesting middle after the Big Bang's wound clock was set, before entropy's final maximization. We are patterns permitted by thermodynamics, eddies sustained by flow, temporary arrangements of matter that happen to be able to ask why they exist. This should not make us feel small, it should make us feel remarkable. We are, in a sense, professional entropy generators. This is our job description in cosmic terms, a role that sounds more impressive in physics textbooks than it might on a CV. But consider what it means. We are part of the universe's evolution, from order to disorder, structures that accelerate that evolution while locally resisting it, complexities that arise because complexity can arise when gradients exist to exploit. The arrow of time enables our existence. It also limits it. Everything that exists because of the gradient will eventually dissipate as the gradient flattens. Stars burn out, species go extinct, civilizations rise and fall, the universe runs down. But that is the distant future. For now, we ride the arrow, patterns in the current, eddies in the flow, minds that emerged from matter and ask why matter behaves as it does. The inheritance we spend is 14 billion years old, and we are only beginning to understand where it came from. We return now to where we began, a cup of coffee, milk swirling in. Once, this seemed mundane, a daily ritual, unremarkable, unexamined. You have watched milk dissolve into coffee countless times without a second thought. But now you see it differently. That milk is mixing because the universe began in an extraordinarily low entropy state 14 billion years ago. The smooth, hot, uniform Big Bang set the conditions for everything that followed, including the arrow of time that makes milk, mixing into coffee, happen in one direction only. Every atom in that cup traces back to cosmic origins. The carbon in the coffee beans was forged in stellar cores. The hydrogen in the milk came from the Big Bang itself. The heat flowing from hot liquid to cooler surroundings is the universe evolving, entropy increasing, the wound clock running down. You are watching cosmic history unfold at human scale. And you, sitting there, observing, understanding, you are a pattern made possible by the same arrow. Your eyes evolved because entropy increase permits evolution. Your brain remembers the milk being separate because memory formation requires entropy increase. Your sense of time passing, your conviction that a moment ago the milk was in the jug and now it disperses through coffee is thermodynamics operating in your neurons. The ordinary has become extraordinary, not because we added anything mystical, but because we traced the connections. The coffee cup is a window into the Big Bang. The mixing milk demonstrates the arrow of time. Your morning ritual participates in the universe's evolution from order to disorder. This is what understanding offers. Not the destruction of wonder, but its deepening. In the inconceivably distant future, the universe will reach equilibrium. Entropy will maximize. All gradients will flatten. No more stars will ignite because no more energy differences will exist to power them. No more life will emerge because no more gradients will remain to sustain it. The cosmos will be uniform, cold, dark, not dramatically dead, but simply same, everywhere and always, with nothing left to happen because happening requires difference. This is the heat death of the universe, the final state toward which the arrow points, but we do not live at the end. We live in the middle, the long, interesting middle, when gradients exist, when structure is possible, when patterns like us can emerge and wonder and ask why. We are the universe comprehending itself. This phrase is not poetic decoration. It is literal truth. Matter is organized through billions of years of entropy increase into structures complex enough to understand entropy. Atoms have arranged themselves into configurations that ask about atoms. The cosmos has produced beings that can trace time's arrow back to its source. That this is possible at all is remarkable. The universe is under no obligation to be comprehensible. The laws of physics could have been different, or there might have been no laws at all. The initial conditions could have been generic rather than special. There might have been no arrow of time, no structure, no mind, no wonder. But here we are, patterns in the current, eddies in the flow, minds that emerged from matter and study how matter behaves. The mystery remains. We do not know why the Big Bang was special. We have traced the arrow to its source, but cannot explain why that source existed. The past hypothesis is required, but unexplained. Physics has answered how, but not why. This is not failure. This is science at its most honest. We acknowledge what we know and what we do not. The frontier is where discovery happens. The mystery is an invitation, not a defeat. Perhaps future physics will explain the initial conditions. Perhaps quantum cosmology will derive the low-entropy beginning from deeper principles. Perhaps the answer lies in the multiverse, or in some theory not yet imagined. Or perhaps the initial conditions are simply given, a brute fact at the foundation of existence, like the fundamental constants, unexplained and possibly unexplainable. We do not know, and that is wonderful. Every morning when you wake, you experience something 14 billion years in the making. The arrow of time that carries you through your day was aimed at the dawn of creation. The direction you call forward, the distinction between what you remember and what you anticipate, the very fact that you exist at all, these are consequences of how the universe began. You are spending an inheritance. Every thought you think, every breath you take, every moment you experience draws on the thermodynamic capital invested at the Big Bang. The gradient is your sustenance. The arrow is your enabling condition. This could inspire despair. We are entropy machines headed for heat death. temporary patterns in a cosmos running down. But this misses the wonder. That we exist at all, that the universe produced structures capable of understanding entropy, is extraordinary. The appropriate response to cosmic physics is not existential crisis, but deepened appreciation. We are the universe organized temporarily into patterns that can ask why it flows in one direction only. We have traced the arrow from coffee cup to Big Bang and back again. We have seen how thermodynamics, psychology, and cosmology align. We have understood that time's direction is not a fundamental law, but a consequence of initial conditions. And in understanding, we have become something remarkable. Matter contemplating itself. Complexity wondering at complexity. The cosmos asking why it exists. The milk swirls into your coffee. You watch and you understand. You are the universe, comprehending itself. Every morning you wake, you participate in a story begun at the Big Bang and ending in eventual equilibrium. The arrow that carries you through today was aimed at the dawn of creation. The past you remember and the future you anticipate are not separate from physics. They are physics, experience from the inside, felt by patterns of matter that emerge because the arrow exists. You are spending an inheritance 14 billion years old, and now you understand where it came from.